So you would have heard about blockchain in the news, on the internet, and really everywhere you go. It might seem that blockchain is the driving force of a new revolution and the answer to all problems. But if blockchain is the answer, what was the question? Because the reality is, blockchain is not a solution for all your problems, and one cannot simply sprinkle blockchain dust on something and make a great and delicious meal of it. Which quickly brings us to the next set of questions. What exactly is a blockchain? What problems does it solve? And why do we need it and not some other technology? Well, a blockchain is simply a state machine, or to put in other words, systems for managing transitions of states. So to use a payment example, in the initial state, let's call it state A, Alice, Bob, and Charlie each had $100 in their balance. A transaction then occurs, say Alice pays Bob $50. The new state, called state B, will show that Alice now has $50, Bob $150, and Charlie $100. So in our state machine example, a set of rules govern the transactions that occur within that system. What we are looking at with blockchain, however, are multiple sets of state machines, distributed across the system and which communicates with each other. So here is one of the powerful elements of blockchain. As a state machine that is distributed across different locations, this can replace a central system and entity when it comes to validating and executing transitions of state. You can understand the state machine as a computer, or what we called a node, and that these computers are distributed all around the world. We traditionally trust central systems like a bank to validate and execute transactions of payment. With blockchain, everyone in the network can validate and execute these same transactions. Trust is now distributed. One of the key areas where you can use distributed trust is within settlements. This can apply across multiple applications, such as in loan protocols for tasks like credit rating verification and automation of payments. In prediction markets, where the censorship-resistant nature of blockchain is used to ensure correct outcomes in prediction markets and forecasting. In federated machine learning, for trustless distribution and verification of machine learning jobs. And in security token offerings for automated settlement of share ownership. So although not the solution to all problems, blockchain has some powerful qualities in specific use cases. To really understand which applications are most relevant and how blockchain is applied to different solutions, it is important for us to understand some of the key technical details. The first thing to understand is how the different state machines or nodes communicate. The method is what is called a consensus algorithm, or a way for the system to reach consensus about a state transition or transaction. There are 3 key points you should note here. Number 1, a consensus mechanism is essentially a set of network rules to check whether a transaction is valid or not. Number 2, it represents a way to elect a leader who proposes which transactions to process. And finally, number 3, it is a way to replicate and validate state transitions proposed by the elected leader and for all participants to agree on the same final version of the state. This leads us on to the second technical aspect, which is to answer the question, how exactly do we know who owns what within this overall system? Here is where we introduce the concept of accounts. And there are 2 main types of accounts, an externally owned account and a contract account. And these accounts all have an address attached to them, which may look something like this. For an externally owned account, this is only accessible through the use of an asymmetric key pair that is owned by a user. A simple explanation of how this works is as follows. A user has to sign a transaction with the private key to change their account state. The private key is only known to the user. Other nodes will verify the transaction's validity by using the user's public key. So those are the concepts of accounts and public and private key in the blockchain world. But what exactly does this mean for the user? Well, let's take a snapshot of how the transaction process would look like. So the ownership of the public and private key pair would allow you to sign transactions and verify and record the transition of account states through transactions. The key point here is the fact that users can authorize transactions themselves in this system. This eliminates the need of central authorities who traditionally would perform these tasks. To bring this point home, let us look at a simple comparison between a traditional bank payment transaction and a blockchain-based payment transaction. In a traditional bank payment transaction, user A would request their bank A, to authorize a payment to user B's account in Bank B. For the payment to proceed, Bank A must authorize the payment and settle the transfer with Bank B through a clearinghouse. As you can see, this includes multiple parties and processes, which increases the cost of the transaction, usually coming in the form of bank transaction fees. Let us now look at the contrast in a blockchain-based payment. User A similarly initiates requests for the payment, but in this instance, they can also authorize the transactions together with other nodes in the blockchain network. The transaction is settled with user B without the need of a bank or a clearinghouse, and therefore eliminating the need of central authorities. At the same time, this eliminates the cost, and as a reference, a typical international wire transfer which would cost $5 would cost 0.017 cents if the transfer was conducted on the Zilliqa network, representing a 99.99% cost saving. Let us now go back to the second type of accounts, a contract account. A contract account is accessible only through invoking transitions stated in the contract code. The contract code can include permission-based transition that only allows users who own certain accounts to interact with it. A contract's transition can even act as a medium to call another contract's transition, thereby allowing for more complex and compartmentalized business logic. So the way it works would look something like this, where a contract owner would invoke the transition. The code is processed to record and verify the state transition from the initial state to the final state. However, as we mentioned before, blockchain is not the magical solution to all problems. In particular, there are certain limitations at this stage of the technology that you should be aware of. Number 1. In order for censorship-resistant nature to hold for authorization and execution of transactions, i.e., making it nearly impossible for people to change the transaction records, having a large number of nodes in the network is required. However, having large number of nodes will result in high overhead and high latency finality. Therefore, blockchains are not very usable at this stage from an efficiency perspective, with transaction per second at around 3 TPS for Bitcoin and 7 TPS for Ethereum. We therefore face a dilemma or trade-off between efficiency and speed with censorship resistance and security of the blockchain network. A second key limitation is the aspect of immutability of the contracts and transactions. So again, the contracts are immutable once deployed, which means that, number 1, no bug fixes could be done after deployment, and number 2, the fact that the code execution is not reversible. There have been notable incidents which occurred in the past due to these limitations. For example, the DAO hack in 2016, where $60 million were lost, and the parity incident in 2017, when $300 million were frozen. So to summarize the technical parts, what blockchain enables is essentially 1. Settlement of simple or complex state transitions, 2. Censorship resistant for requesting, authorizing, and execution of transactions, and 3. Cost savings by eliminating the need for the middleman and central authorities. Ultimately, it forms a foundation for the era of decentralized finance. So now we understand the key features of blockchain and its impact in decentralized applications across a variety of industry sectors such as financial services and supply chain. One of the key problems is that the usefulness of these applications are limited by current blockchain protocols which are not scalable. Well, this is where Zilliqa comes in. Zilliqa is a next-gen high-throughput blockchain platform. In essence, it is a scalable smart contract platform capable of processing thousands of transactions per second. That scalability is enabled by a technique known as sharding. Imagine a mining network with 100 nodes. Zilliqa would divide the network into 10 groups, called shards, with 10 nodes per shard. If each shard processes 10 transactions per second, then all shards together can process 100 transactions per second. By this logic, if you increase the number of nodes, the throughput increases. The increase holds a linear relationship to network size, So with more nodes in the network, transaction per second rises at an increasing rate, similar to what you see in the diagram. Zilliqa has also developed a new smart contract language that is matched to its use of sharding. This domain-specific language, Scilla, is non-Turing complete, is amendable to formal verification, has clean separation between communication and computation, and has structured recursions instead of loops, so all programs terminate and hence are decidable. So to visualize what technical problems Zilliqa solves, let's go back to our diagram of the dilemma of blockchain. Zilliqa would be placed right about here, with reasonable latency for finality, around 1 minute block time, low overhead, around 2,000 transactions per second, and large number of nodes of around 2,400 nodes. To encourage and enable developers to actively participate in the Zilliqa community, there are a range of developer tools established in the community. These include SDKs for JavaScript, Java, Go, Ruby, and C# languages, hosted API servers for your decentralized applications, as well as analytical tools for visualization of your transactions. In the final part of this video, we want to provide a brief tutorial on how to develop applications with Zilliqa. We will take you through the process of creating a smart contract in 12 simple steps, and along the way, we will introduce the tools which have been developed to make it easier to use for aspiring developers. So you may find that starting off the development of smart contracts can be a hassle, and often there are several tools that you have to install even before you can start coding. Another problem is the need to keep up to date with any tools that change midway during development. In order to address these exact pain points and make the process of smart contract development more effortless, Zilliqa established a web-based interactive development environment, or IDE, that comes with all the necessary features required to manually create and test contracts. The IDE link can be found as follows, noting that it is optimized for use in the Chrome browser. So here is a look at the web IDE, which will be the primary portal. The key features included in this IDE include: number 1, persistent memory, as all contract codes and contract states are stored within your browser's cookies until you clear them with the IDE's refresh button. Number 2, testing accounts, where the IDE is equipped with 20 different accounts that are preloaded with 1 billion test Zilliqa tokens. A developer can use these accounts to deploy and call contracts written in the IDE and check if their contracts are working as intended. Number 3, automatic filtering of transitions, such as functions and methods, which filters out the callable transitions available within the contract automatically after you deploy it. Number 4, static type checking, which type check for errors in variables within your contract on the fly and ensure that the contract is type safe before deployment. And finally, number 5, automatic block time, as the IDE simulates a blockchain, literally a chain of blocks with timestamps on them, and sets an arbitrary block interval at 10 seconds each. A developer can use this block time as your timestamp for your time lock or escrow contracts. So the steps for developing a new smart contract typically goes like this. Firstly, you can create a new Scilla file by using +new contract and naming your project. You can then code in Scilla, referencing a comprehensive range of documentation or sample contracts on the left-hand side tab. In this instance, we can use the Hello World pre-established code as our example. Click on Save and check on your contract for type and syntax errors. You can debug using the red error pointer highlighted in the coding environment. You can choose an arbitrary account. And at the Deploy tab, you may key in the initial parameter of the contract. After which you can deploy the contract. You can then choose an arbitrary account again. At the Core tab, key in the message parameters to pass to the transition of the contract. Next, call the contract. At the State tab, check the previous and final state of the contract to see if the logic flow is correct. You may repeat step 5 to step 11 for each test case of your smart contract. For further information, you can check out the developer portal in the link below. Now we come to the end of our video course. We hope you now understand the magic and limitations of blockchain, some of the key technical parts which makes it such an interesting and powerful technology with applications across many industry sectors. We also hope you were able to learn a bit about the exciting development within the Zilliqa community, the technology that has been built and the developer tools that are available to ease you into the community.